And I had the pleasure of working with, these amazing, I would call them visionaries, Vivek, Alan, who are really trying to do very ambitious things. So one is, trying to build an AI doctor, and more recently with this co-scientist project, trying to build, a prototype towards an AI scientist. I've already been convinced, like seeing the system at play, that it really can do that. You talk to any of these scientists, like they get so excited when they get to see the outputs of the system. And it's also, to me, it's the worst it'll ever be, right? It's constantly getting better. The models are getting better. Our methods are getting better. So, I'm just really excited to see where this road goes, and I want to be a part of it. My name is Anil Palepu. I'm a research scientist at Google Research. I'm going to be talking about the recently published AI Co-Scientist, a multi-agent system for novel hypothesis generation. So this is the preprint that came out about a month ago. And as you can see, it was like a very, very huge collaborative effort from Cloud AI Research, Google DeepMind, as well as many external collaborators, hospitals, Houston Methodist, Sequum, all of these different places. So I want to stress that I worked on mainly the technical aspects of it, and even then there's many people who can speak more to it, but I will also try to touch upon some of the applications we've done in these three biomedical areas. I think the focus for today's talk will really be about the system itself. Here's just like a diagram. It's our first figure in the paper describing what the system does. And kind of at a high level, essentially you have, so this is a user-facing system, right? So the goal is we can have scientists input some research goal, and this can be oftentimes like pretty generic and pretty underspecified, but they can provide their research goal, maybe they can provide some restrictions, like this is my laboratory setting, this is the kind of extent of things I can do, this is the attributes I want to require of hypotheses, such as, I want them to be novel, I want them to be, testable, so on and so forth. But essentially, our AI co-scientist takes it from there, and it generates this plan configuration here, right? And then it has a multi-agent system, which will kind of over time, and this is like by over time, I mean over the course of a week, maybe even longer, continuously generate hypotheses, reflect on those hypotheses, and rank those hypotheses so that in the end, you kind of have this tournament where the top ranking hypotheses, hopefully, very actionable and hopefully very high quality and verified. So this is kind of the system. Essentially, like in the end, we can give those hypotheses back to the scientist in this ranked list of different research directions and top hypotheses. And the hope there is, right, those are useful for them to go and take and test in the laboratory. So at the moment, our endpoint, right, is the hypothesis itself. Of course, potentially this could be extended, further in the future. And so that's a system. And so in this paper, we kind of tested it in three different domains. These domains kind of varied in their complexity and scope, right? So the first domain was for drug repurposing. So for leukemia, we were looking at if we can take a set of existing drugs. So these are already approved and can be used for other indications. And we want to see, can we repurpose these drugs for AML? The goal here is to generate some hypotheses which can explain why, a certain drug might be useful in various AML cell lines. The second idea was around novel treatment targets for liver fibrosis. Here we were looking at the epigenetics and trying to see, can we propose different targets based on the epigenetics that would be helpful in treating liver fibrosis. And then finally, this last hypothesis, and honestly, this is the part it's starting to get very bio-heavy, and I lose a little sight of it. But essentially, we had a collaborator who had a very specific hypothesis about, or had a very specific research area in this CFPIC eyes. This is something that is a genetic element that's related to antimicrobial resistance. And essentially, they had, for the past 10 years or so, been researching this area and had finally come up with some certain understanding of how exactly these are working from an evolutionary perspective. That had not been published, and essentially what we had done is we had the prior research up to that point, and we showed essentially the AI co-scientist was able to recapitulate those findings, and so these collaborators were very impressed as to how the co-scientist was able to come up with a very similar hypothesis in the span of 2 days. In addition, I think the other kind of interesting thing is the other items on that ranked list were also, they said very compelling and just useful to think about as well. That's kind of an overview of the system, the applications we talk about in this paper. But yeah, like as I mentioned, I think this talk will be mainly about the system, so I'll kind of get into it. The AI co-scientist can kind of be broken down into four main parts. So the first part is the natural language interface. How do scientists interact with the system? And there are a few ways actually beyond just inputting that original goal. Second is an asynchronous task framework. So basically, we want this co-scientist to be, continuously working essentially, and as I mentioned, in the span of weeks. And there's many different things you can do, and I'll talk about some of those things later. But essentially, we have some kind of supervisor which is overseeing the work of the AI co-scientist, and what weights to assign to what tasks and when to do what. In order to ultimately, come up with the best hypotheses. Finally, we have a set of specialized agents, and these are, shown in this box here. We have agents to generate, agents to do review and reflect, agents to kind of run this tournament and figure out what the best ideas are, agents to iterate on ideas, agents to cluster ideas, an agent to kind of do an overall summary of the set of ideas and try to, create this research summary. These are all kind of working at various times in different weights, and essentially this is used to produce the set of hypotheses. So first, the natural language interface. So as I mentioned, the scientists will input a research goal, and that's one thing they can do, and that kind of sets off this whole process. That research goal will be turned into a certain research configuration. So your research goal could be input in free text. It could be really simple. You could provide some of your constraints as well, but essentially that will be turned into this kind of structured format. We're going to list what are what is the research goal, and that can be reformatted by the AI co-scientist itself to maybe make it more clear and more actionable. And then also, what are the attributes we want to measure? So these attributes are going to be things that are going to be used by the specialized agents to kind of rank hypotheses, and that can vary per research goal. Like, I think most research goals will have goals of like novelty and correctness and testability. But for a certain domain, there might be a very specific attribute that you want to measure, and that can also be automatically decided upon by the AI co-scientist. That configuration will basically be sent to the supervisor agent and be used to set these agents and get them working. But in addition to that, the scientists at any time can, adjust their research goal. They can also, input their own hypotheses into this tournament, and those hypotheses can be ranked again by the ranking agent, and basically they have kind of the ability to provide their own input into the system. So this is an example, like a really simple example of a configuration. The goal might have been develop a novel hypothesis for the key factor, blah, blah, blah. And essentially that will be parsed. And so here they're parsing the preferences. So we want to focus on novel hypotheses, and we want to focus on the mechanism of action for these NPCs. And then here the attributes we want to measure: novelty and feasibility, and constraint should be correct, should be novel. Again, these are like kind of more bread and butter attributes and constraints, but for your task, you could specify some more strict constraints. And then, the researcher can refine their research goal. They can input their own hypotheses as well. So the next part of this is the asynchronous task framework. So again, the configuration will be sent to the supervisor agent. And at the start, the supervisor agent will basically tell first, let's start generating a set of hypotheses. And so they'll assign a high weight to the generation. But then, over time, it will start to ask for certain hypotheses to get reviews, right? So the top ranked hypotheses, it might want to do a very deep review. The lower ranked hypotheses, it might, just do a very simple zero-shot review. And similarly, like it is also controlling like which hypotheses to compare. So, the top ranked hypotheses we may want to compare more to get a better signal for that ELO, whereas like the lower ranked hypotheses, which have already been kind of looked at already, don't need to be considered as much. And so it's controlling basically which agent to call with what focus at what time, and it's doing that continuously over the course of while a research goal is loaded, and eventually like either you can stop it if you've decided, hey, I've done this enough, or at a certain point, we tend to stop it after it's generated a sufficient number of hypotheses. Finally, like this entire set of hypotheses will be summarized with the research overview. And just to point out that we actually provide like different things to the scientists so that they kind of don't need to look through this list of like thousands of hypotheses. They can kind of get a summary of these are the main research directions, and these are some of the things we're thinking about, especially with those top goals. So now to get into the specialized agents. So as I mentioned, these 6 different agents. So we have the generation agent, and so this one, its goal is to generate hypotheses that address the various research goals using various methods. By various methods, I mean we really can change many things. So we can change the model that's being used to generate. We can also change the method. So, from as simple as like zero shot to let's scour the literature, to doing some kind of self-play debate, to kind of come up with hypotheses between like 2 agents. And all of these have been implemented. And this is kind of this is something that we can grow, right? There can be more methods, whatever we want to do to generate the hypotheses. We can design a method and add that option to the agent. At the start, we're going to be focusing a lot on this, and this is going to have a heavy weight as dictated by the supervisor. Another really important part is the reflection agent. And so here, basically all those attributes we talked about, the reflection agent is going to be looking at each hypothesis, and it's going to be generating correctness, quality, novelty, and it's also going to be, for certain hypotheses, doing a much deeper review. So like for all hypotheses, it might do a very simple zero shot kind of generation of this, but for hypotheses that end up being ranked higher, it might do different methods. So one thing is a deep verification. Essentially, that's where we take a hypothesis, we break it down into its constituent assumptions. We even might break those down further and kind of decontextualize them. And essentially, that deep verification step is going to verify, each step of each like sub assumption of that hypothesis. And so for the top ranking hypotheses, we kind of want to do this very careful review to make sure that there's nothing that's actually like going to disqualify that idea. In addition, another aspect of the reflection agent is, we also ask it, does this hypothesis explain any previously observed result? That's another aspect of if this hypothesis can explain something that has been observed, that's another point towards maybe it's a useful hypothesis. So that's the reflection agent. The ranking agent is basically running the tournament. So again, this is an ELO-based tournament, meaning we're comparing 2 hypotheses head to head, and the winner will go up, the loser will go down. Essentially, here the main method we use. So again, we can choose something different for the low-ranking hypotheses versus the high-ranking ones. For the low-ranking ones, we usually do something very simple, like a zero-shot comparison. But for the high-ranking ones, we often use a debate, where we'll have 2 agents discuss the 2 ideas and go back and forth to decide, which hypothesis they prefer. And this is, again, like all kind of based on, the reflections, based on the generation, based on like the hypothesis, as well as whatever attributes have been specified that we're trying to prioritize for this research goal. And then there's a proximity agent. So this one kind of is doing something different, which is just trying to cluster ideas. And so essentially, the benefit here is we can kind of get a group of ideas together, and then that can kind of simplify some of like the review process, where we don't need to actually be comparing every single pairwise idea anymore. And kind of just simplifies that space a little bit. The evolution agent is similar to the generation agent in that it's creating new hypotheses, but basically it's taking these existing ideas and trying to iterate them in some way. And so oftentimes this is looking at the reviews of those hypotheses and trying to explore through further literature searches or something like that, trying to improve those ideas so that they should address the kind of reviews concerns. And then there's the meta review agent, which is looking at all these reviews, maybe within a certain cluster, for example, identifying patterns in the tournaments and top hypotheses, and just kind of summarizing, overall what is happening in this tournament. Finally, like there's this context memory. So essentially, like all of these. So I think one thing that's really important to note, right, is we're using this long context Gemini. really none of this would be possible without this. So we're stuffing like tons of reviews and basically everything we're generating into each model call, right? So that relies on long context, and basically everything, like all the hypotheses, all the reviews, everything has been being written to disk, and we're constantly like pulling in the right thing from the right agent at the right time to basically aid in that specific agent's task at that moment. I think that long context aspect is really like critical to all of these agents, actually. So we run this tournament. We're comparing pairwise hypotheses. Essentially, we get this ELO score. I think it's interesting to note in our paper we show that the ELO rises with scaling test time compute. So essentially, we took our set of ideas that we had generated up to that point for the different research goals, and we bin them. For each research goal, we bin them into time buckets. And essentially what we found was that, as expected, right, the ELO tends to go up over time. I think what is kind of interesting is we didn't really get to the point where we saw this level off. Again, we had been running this for a week, right, each goal. So it was kind of interesting that we didn't see the ELO score leveling off at all, it seemingly. But the other interesting thing is, one could argue like, hey, does this actually mean anything? The model's auto evaluation is saying it's better, but does that actually mean that it's actually better, right? I think that part is unclear from these alone. So one thing we tried to do to test this was we basically evaluated we treated each question in the GPQA diamond set as a research goal, and we had the co-scientists try to solve each question. And what we did find is that there was a strong correlation between the ELO rating and the accuracy on these GPQA questions. So basically, like the hypotheses that led to correct answers tended to be higher ELO rating than those that had incorrect answers. Just to touch upon some of the applications. So for drug repurposing, the goal here was to explore repurposing for leukemia, right? And so we looked at, this was actually for a broader set initially. So we looked at 2,300 approved drugs across 33 cancer types. Here, I think one interesting addition that we did for this specific application is we integrated DepMap. And so this essentially is the probability that a certain gene is essential for a given cancer cell line. And so we use this actually to aid in that review and basically filter out hypotheses. We took these set of hypotheses and we generated from these hypotheses, we actually generated a more detailed specific aims page. So this is like a page you would give, when applying for a grant or something. And we gave these to clinical experts and had them evaluate kind of these qualitative aspects of the specific aims to try to see, how good they were. And we did find that they tended to receive pretty positive reviews in terms of, not just the clinical aspects, but even just like the writing of it. And there seemed to be some confidence that, this could lead to like a successful grant. In terms of like that aspect, they seemed favorable. Of course, we wanted to actually, test some drugs. So we did some wet lab validation. And so here's where we focused on AML, just based on our collaborators' expertise. And we essentially took a set of, I think, 15 of hypotheses and asked them, which ones they wanted to test. We tested a few different drugs, and what we find, so these curves are basically showing for a given cell line, the viability of those cells at a given concentration of the drug. And so, when it goes down, that's basically telling you that like that drug is effective in treating AML at that concentration, at least, in vitro. We can see that, the two of these drugs that were proposed, and I think a few more actually, were successful in treatment in various AML cell lines. So I don't know how to pronounce this, but this drug and Kira-6. And I think this one was actually shown in several different cell lines to be quite promising. Novel target discovery. So here we were asked to produce testable hypotheses on epigenetic targets for liver fibrosis. So we selected from 15, 2 of the 3 epigenetic modifiers were actually successful. So you can see, so there's 4 here, but there are actually only 3 epigenetic targets. these two, which I think we have another paper which actually lists what specific drugs they were. I don't think this is one of our collaborators that just preprinted this. But essentially, a high proportion of the drugs that were proposed were actually successful in reducing in having antifibrotic activity. And then finally, this antimicrobial resistance application. So yeah, these CFP-ICIs are these capsid-forming phage-inducible chromosomal islands, which were thought to be involved in antimicrobial resistance, and the exact mechanism was not unclear for a long time, and that's what our collaborators, Jose, what they were kind of working on for the past decade about. And essentially the AOK scientist was able to come up with not only that hypothesis that they ended up discovering pretty recently, but also, again, several other hypotheses that they found quite compelling. So it's a bit qualitative, but I think this is an exciting, promising thing to see. And to kind of conclude, the AOK scientist is a general purpose multi-agent system for generating novel research hypotheses. It can, I think one important thing is we are designing it to really work with humans. So it can take human input, they can provide and revise research goals, help select promising hypotheses. I mean, ultimately, it's called co-scientist, and I think that's the key, right? Is in a lot of our cases, we would generate the top 15, top 20 hypotheses. Our collaborators would use that to kind of select, things to test based on their own intuition. And it did really function more collaboratively than I think independently, but it was able to do some of this deep research that would have taken these scientists a very, very long time to do on their own by itself. Second is it has access to external tools. So in our case, primarily leveraging web search and looking at literature, but in the future, you can imagine that you can integrate really any kind of domain-specific tools for a specific research goal. In the paper, we do explore AlphaFold, but this could be very general and could apply to whatever tools you're able to call with an API. Thirdly, inference scaling. So I think one difference between this and something like deep research is this system is built to iterate for days. I mean, it's obviously probably really expensive to get these final set of hypotheses, but I think from operating for days and doing all these detailed steps from generation to review, we see that the ELO continued to improve. We're not really getting into the state where we feel like we're reaching some asymptote, at least to the extent that we ran it on these cases. Of course, our ELO, again, we need to be sure that that's actually that ELO continuing to improve actually correlates to a truly better hypothesis. That part is pretty unclear. But that being said, operating on this kind of time scale really does change the game in some ways. And I think the fact that we had these very diverse set of specialized agents, each with different roles, different access to tools and goals, right? So I think having this set of these agents operating with this asynchronous execution allowed us to create these rich, diverse, high-quality hypotheses and not kind of narrow in on the same set of things. It kind of enabled continued diversity. The applications to be demonstrated are really wide in terms of their complexity, and I think again, this is a general purpose system. It doesn't have to be used for biomedicine. We've tested it for many other things, and it seems to work pretty well, actually. I think it is pretty promising that, across, at least in biomedicine, across, some very different problems, we're able to get promising results according to not just us, but, the actual scientists that work in those spaces and believe that this is useful for kind of aiding in their discoveries. Thank you for listening.